Hi there, and welcome to our physics class. Today we're going to be talking about the second law of motion. This is our kind of our recap of our lesson that we've been doing and kind of what we did in class on, let me think about this, both Tuesday and Thursday to review for our upcoming quiz. So a few of these things are pretty straightforward, and a few of them maybe take a little more effort and work to work through, but that's okay. So when we started a couple weeks ago, or really last week, we asked you what you knew or remembered about Newton's second law of motion. And we had answers from anywhere from I don't remember anything, things like nothing, to people talking about, oh, I think it has something to do with force and maybe mass and maybe acceleration. And there was some recognition that those kind of words did come up at some point in your prior studies. When you talked about the second law of motion as a formula, we did say that it was equal to the net force of an object is equal to the mass of an object times the acceleration of the object, or F equals ma. We can also write that in different ways. We could find the mass of an object by saying that it is the net force of an object divided by the acceleration. And the acceleration of an object is found by the net force divided by the mass. Just recall again that this symbol here, sigma, is standing for the net force, which means the combined forces in a single direction, right? Oftentimes we're talking about things maybe working along the x-axis here, and we want to know all the forces that combine to make that net force. So if this was a 5 newtons going this way and a 2 newtons going this way, we would have a net force in this case of 3 newtons going to the right in that direction. And the same works for moving vertically as well. So we were looking for the net forces when we are working with the force formula here, as Newton talks about. The other thing that came up in our lesson was talking about weight. Weight is often referred to as our FG value. Often when we're doing our components, we have vectors going this way. We have our normal force here, and we have the force of gravity kind of going this way. So FG is that weight value, and that's found by taking the mass of an object and multiplying it by the gravitational force, the gravity force, or in this case, we would usually say M times GFS equals Fg. And you may have learned it just as simply gravity. Either way, we know that we're taking the mass of an object and we're multiplying it by the gravity force, which is 9.8, to determine what the Fg value is going to be. And we're going to need to do that in several different problems in this activity as well. Sometimes they're going to give us the Fg. When you calculate this, this does turn into a value that's measured in newtons. So sometimes they'll give you something that has like a Newton value, 20 newtons, and they'll ask you to find out what the mass is. In that case, we're going to work backwards to find the missing variable of mass by dividing 20 by 9.8 to find out what the mass might be. So that has come up, so be ready for that as well. Couple more little points, just kind of recapping. This was a sixth grade skill actually, but converting grams to kilograms. Just recall that there are 1,000 grams inside of 1 kilogram. And if you're taking something like a gram and needing to convert that to kilograms, we're going to take the decimal and we're going to move it over 3 spaces, 1, 2, 3, in order to rewrite that as kilograms, as so. So if I had something like 74 grams and I asked you to convert that to kilograms, we're going to move 3 spaces, 1, 2, 3, put our decimal point there, hold the space with a zero, and I have 0.074 kilograms to convert that. We always could go the other way as well, right? If I had 83 kilograms and I want you to convert that into grams, we move the decimal to the right, it's 3 places, 1, 2, and 3, holding the 0 spaces and adding our decimal there to convert that into grams from kilograms. One final note is sometimes we do talk about things in scientific notation. Generally with scientific notation, we're going to be using just the first 2 digits of a number, and we're going to be putting a decimal point right there. And we would rewrite this as 3.5 times 10 to a certain power. Now that certain power is determined by how many decimal places you have to move the decimal point. In this case, we're moving at 1, 2, 3, 4 decimal points. So this is 3.5 times 10 to the fourth power written in scientific notation. So if I had a number like 8675309, and I asked you to write that in scientific notation, you would start here and say, well, we know we're going to kind of end up at that spot. So we're gonna have 8.6 times 10 to some power. Let's see our hopping. We go 1, 2, 3, 4, 5, 6. So 8.6 times 10 to the sixth power if you were to rewrite that in scientific notation. And of course, this does work the same way if you're trying to make it into the real number. If you had 3.1 times 10 to the third power, then you'd write 3 and a 1. And instead of having the decimal here, we're going to move it over 3. 1, 2, 3. And then fill in with some zeros there to rewrite that as a regular number. All right, so let's take a look at some of the things that were on your Edgenuity lesson from this week. We had, first of all, a demolition of a building, and a 1,300 kilogram wrecking ball hits the building at 1.0 meters per second squared. Calculate the amount of force at which the wrecking ball strikes the building. So in this case, we're going to use our formula of the force equals mass times acceleration. And our mass in this case is 1,300 and our acceleration is 1.07. And so when we multiply 1,300 times 1.07, we end up with the force equal to 1,391 newtons. That's just kind of a little recap on calculating force. Another problem we had was to look and see an eagle accelerates at 22.35 meters per second with a force of 120 newtons. Disregarding other forces acting on the eagle, such as gravity and air resistance, calculate the mass of the eagle. So our formula for calculating mass is that mass equals the force divided by acceleration. So our force was 120. Our acceleration is 22.35. And so when I do 120 divided by 22.35, I end up with 5.36. Because I want the nearest tenth, I'm going to look at the number next to the tenth, which is the hundredth place. It's greater than 5, so we're going to round up and make this equal to 5.4. And this is going to be mass, so kilograms there. On our next one, it says Sachi wants to throw a water balloon to knock over a target and win a prize. The target will only fall over if it's hit with a force of 0.035 newtons. The water balloon has a mass of 11.4 grams. That's critical there. How fast will Sachi have to make the water balloon accelerate to hit the target? So we are looking at acceleration. Acceleration is found by doing force divided by the mass. But notice that our mass in this case is 11.4 grams. We want to convert that into kilograms. So kilograms, we're going to move the decimal place to the left 3 spaces, 1, 2, and 3. And so we actually have 0.0114 kilograms, not 11.4 grams to use. So the force is the same, 0.035 divided by 0.0114. And that becomes our force divided by our mass, which in this case equals 3.07 meters per second. Okay, and that's that one right there. So that's our meters per second for acceleration. And now we've done one of force, one of mass, and one of acceleration. And as I said in class, it's always good to talk about the elephant in the room, not to just ignore them, but there is an elephant in our classroom from time to time. And if we had to calculate the FG value of the elephant in the room in our class, we're going to take its mass of 5,235 kilograms, and we're going to multiply it by the gravitational force of the Earth. So that is our mass times our GFS, basically. And when we multiply that out, 5,235 times 9.8 gives us a lovely number of 51,303 newtons is the force of that elephant in our classroom. You can all look around and notice who that elephant might be. No, that's a joke. That's not a person. It's just a metaphor. There's no real elephant in our classroom. Or is there? I don't know. Stay tuned. Dun, dun, dun. Okay, now let's move on to our more complicated problems. These are the ones that you maybe got a little stuck on. So first of all, it says 2 children, and notice it's 2 children, are pulling and pushing a 30-kilogram sled. The child pulling the sled is exerting a force of 12.0 newtons at a 45-degree angle. So this is our first one here. That's our first value. This is the first kiddo pulling this way here, 12 newtons this direction. That's one of our vectors there. The child pushing the sled is exerting a horizontal force of 8 newtons. And so I'm going to just do a different color here because this is a whole different vector, different person, right? Two people are pushing or pulling on that sled, and that's our 8. There's a friction force of 5. So we have 5 going this direction here. So when that's going the wrong other way of 5. First question asks us, what is the weight of the sled? Now, the weight of the sled is calculated by doing our Fg value, right, times the mass times the gravitational force. Now, we have a mass of 30 and we have a GFS of 9.8. And so the FG in this situation is going to be 30 times 9.8, which is 294 newtons. So this value down here is 294 newtons for our FG value. Okay, that's our weight of our sled. Looking pretty good so far. So when you turn the page, on my case here, it's our 294. The next question says, what is the normal force working exerted on the sled? Now, normal force is going to be the force that is moving, in our case here, up this direction here. This is our normal force. Now, our normal force, because the sled is not flying in the sky and anything like that, is going to be equal to the Fg force, except that we have some other vertical forces in play. Essentially, what we want to say is that the net force in the vertical direction is going to be balanced here. It's going to be equal to 0, meaning that when I take the normal force, okay, if it was just normal force, and I add to it another value, which we'll talk about in a second, and subtract from it the Fg, I should be at 0. This other value is really the key component of this problem or this part of the problem. Because if I look over at my people that are pulling and pushing, person number one is pulling or pushing in a pure horizontal direction. So there's nothing vertical about that. So I don't even have to worry about person number one in this part of the problem. But person number two is pushing at with 12 newtons of force at a 45-degree angle, which means that there is a component in the vertical direction. If I was to separate this, think of this as its own little problem like this, like so. And we have 12 there, and we have our right angle, and we have a value here of 45 degrees. My other vertical force, this is my FP2. This line here is my FP2 in the y direction. My FP2 in the y direction can be found by noticing that it is the opposite of the angle. So this value, this line, which is this part here, needs to be included with my equation for the FP2y because both of these are a part of the kind of the vertical going up values. The sum of these needs to be equal to the Fg value here in order to have a net force of 0. Does that make sense? So we're going to have the Fn, the normal force, when combined with this component, is going to be equal to Fg. And that's really what we're saying here. So those two lines are going to be equal to this one line. So I need to find out the FP2y value, this value, in order to then use it in the formula to figure out what Fn could be. So to find this one here, because I'm doing the opposite, that's going to be a sine of an angle equals the opposite over the hypotenuse. In our case here, because we're solving for the opposite, we can also say that it is the hypotenuse times the sine of an angle equals the opposite. So now let's put the numbers in, or the variables for what we know. The hypotenuse in this case is 12. The angle is 45, so we're going to say sine of 45 equals our opposite, which is what we're looking for, our FP2y value. So 12 times the sine of 45 is going to give me a value of 8.48, approximately that, for FP2y. Now in this case, now that I have this value here of what FP2y is, 8.48, I know that my FG is equal to 294. My FP2Y is 8.48, and the FN is what I don't know. And now I can make that all equal to 0 because it's going to be balanced out like we have right there. And so if I add 294 to both sides, 294, 294, then I subtract, well, first of all, I would say I have Fn plus 8.48 equals 294. And then I subtract 8.48 from both sides. F of n, or my normal force, is going to be equal to, in this case, if we did the actual math, let me get out my calculator real quick. 294 minus 8.48. I'm going to have 285.52. And we want to round that up to the nearest whole number. So we're going to say 286 newtons of force is my normal force going this way. Which, again, if you think about it, makes sense, right? 286 plus about 8 or so is going to be 294, right? 286 plus about 8 is 294. Again, we're losing a little bit because we are rounding, but that's going to be that same value and it's normal and we're good to go. So that's the idea on the normal force, okay? So for the normal force, we did not worry about person number 2 or one's pull because it was strictly horizontal. But we did had to account for this vertical component of pull number 2 because it's going at a diagonal. That's going to come into play with the next part of our question. Okay, so let's go to this next one. We know our normal force is 294. We know that our FG is 294. Our normal force is 286, which is not going to be important for this next part, but just going to jot it down there. The next part is our acceleration. Keep in mind that acceleration happens along the x-axis. So to find the acceleration, I want to look at all the vectors that are going this way or this way to find the net sum, the net force of all those vectors going this way or that way. So a few things I have. I notice that I have this vector here for the force of friction, right? That's one vector that I have. But I also have then a few more. I have pole number 1, this person right here, with a value of 8. All right, so I know I have pole number 1 with a value of 8. That's one of them. And I have this guy going the other direction for the 5. But I also have this diagonal one. And so once again, let me draw my diagonal one just separately so we can pull it apart. And here's my 45 degrees. We know that's 12. I have for my FP2 person, I have an FP2 in the X direction. I need to also include this value right there because that's one more vector on the horizontal direction that I need to include to find the net pull in the leftward direction. So I'm going to have to include this vector, and then subtract this vector here. You see, this blue vector that I just drew is, in a sense, right here. It's part of this one. It's not part of, it's part of this triangle, right? So there's really kind of two vectors side by side or on top of each other working in that way, except it's a component vector, so it doesn't actually exist, but I'm going to draw it separately just so we can see we're looking at 1, 2, 3 vectors there. So to find this vector part here, this is going to be the adjacent side, right? So the adjacent is going to be using cosine. The cosine of an angle equals the adjacent over the hypotenuse, or written another way, the hypotenuse times the cosine of an angle equals the adjacent. In this case, my hypotenuse is still 12. My cosine is going to be cosine of 45, and that's going to equal my FP2x. And what's interesting about this, if you know a little bit about how your trig ratios work when you're doing a 45-degree angle, is that you end up with legs that have the same value. So this 8.48 is just like our sine of 45. And that's just because it's a 45-degree angle for FP2x. Now, in terms of our net force, and it doesn't really matter how it is, but I'll go ahead and do it the way we've been doing it. This is again, it's gonna be balanced, right? We know it's gonna be balanced. We know that much. So I have my force of friction is my positive one because it's on the right side of the kind of coordinate grid. So I have the 5. I'll write this one here. I'll write it here. The force of friction minus the force of pole number 1 minus the force of pole number 2 in the x direction. So I'm going to take this value and subtract the green arrow and subtract the blue arrow. So my force of friction is 5. My force of pole number 1 is 8. And the force of pole number 2x is 8.48. So I have 8 plus 8 is 16.48 minus 5 gives me a negative 11.48. And because we're dealing with forces, we can't actually have a force that's negative. So we're going to kind of think of the absolute value of that and make that a positive. 11.48 is my force. The question, though, asks us for acceleration. Acceleration is found by finding the net force divided by the mass of an object. Well, now we have the net force in the horizontal direction, and we have a mass right there. So our acceleration is going to be equal to 11.48 divided by 30. And in this case, 11.48 divided by 30 is going to be equal to 0.38 meters per second squared. And that's how we solved that very, very complicated problem, right? There's several parts to that one. So make sure you're getting the idea of how that all works there. All right, let's take a look at the next one. This lawnmower one, a little tricky too. It says a boy is exerting a force of 70 newtons at a 50-degree angle on a lawnmower. He's accelerating at 1.8 meters per second. Rounding out the answer is the nearest whole number. What's the mass of the lawnmower? Well, in this case here, the mass of the lawnmower is found by determining, well, how much force am I pushing in this direction? Because the lawnmower is moving in a horizontal direction. So if I can determine this value here, my FPX, I can use that to determine the mass of this object. Okay, because that's the lawnmower is moving in horizontal direction. So however much I'm pushing it this way is going to be related to the mass of that object. Okay, that's one way of thinking about it there. So in this case, our FPX value is going to be equal to, for thinking about here, this is going to be adjacent. So this is going to be the hypotenuse times the cosine of the angle, right? The hypotenuse. So the adjacent is equal to the hypotenuse times the cosine of the angle. So we have 70 times the cosine of 50, which equals 44.9. So this value right here is 44.9 for the force it takes to be moving that lawnmower that direction. That's a force that we're going to use. Now that force there is going to help me determine what the mass of the object is going to be. And that's our goal, is to find the mass of the object first of all. So mass is equal to, remember, the net force divided by the acceleration. And we're going to find the mass of the object. It's moving in a horizontal direction by finding the net force in the horizontal direction. So we're going to do 44.9 divided by 1.8. And 44.9 divided by 1.8 is equal to 24.99, but the nearest full number, of course, is 25. So we're going to say the mass is 25 kilograms for that object right here. So our lawnmower is 25 kilograms. That is the mass of the object. Okay, oops, too far. So we know we have an object that weighs 25 kilograms, and now it wants to know what's the normal force exerted on the lawnmower. Well, a normal force is going to be the force acting above kind of our kind of horizon line. So we know we're pushing the lawnmower and we're pushing it we can see by the arrow vector down. So I'm actually put my normal force up here because this is my kind of vector going this way, my force normal. Everything below this line, horizon line, is going to be kind of in the negative direction. So I have a couple things I'm looking at. I have the vector going this way, which is my FG, but I also have this component right here for part of the triangle to find out what this FP in the Y direction is going to be. And so my normal force, because we're having something that's going to be, the net force is going to be equal to 0, my normal force minus the force of Py minus the force of G is all going to be equal to 0. Another way of thinking about it might be, if it's easier, to think that the normal force is simply equal to the force in the P of the Py plus the force of G, if you rewrite that around, okay? So that's what we're looking for. Now, I actually already know my force of G, or I can figure out my force of G. My Fg value, remember, is the mass of an object times the gravity. The mass we said was 25. So 25 times 9.8 gives me my Fg value. And so my Fg is 245 newtons. So I can plug that number in right there, 245 newtons. I'm looking for the normal force. So the next value I need is my FPY. Well, that's my triangle. And we have a 50-degree angle. We have a hypotenuse of 70. And we're looking for FPY, which in this case is the opposite. So that's going to be the hypotenuse times the sine of an angle equals my opposite. So 70 times the sine of 50 equals my FPY. And 70 times sine of 50 is equal to 53.6 for our FPY. So now we can use that number and plug it in over here, 53.6. So 245 plus 53.6 is equal to, in this case here, 298.6. Or if we're going to round that to the nearest whole number, we would say our normal force is equal to about 299 newtons. So what that includes then, once again, is I have the normal force here, right? This value here is going to be equal to the force of gravity and the force of the exertion pushing the lawnmower in that downward motion. So these two vectors here combine to equal this one vector there. I know they don't look like it because it's just a picture, but that's what we're trying to say overall when we look at this stuff here. All right. So that's the lawnmower one. Let's do a couple more that you're going to need to kind of have an idea about how to do for your upcoming quiz tomorrow. It says an object is pulled right by two forces, has an acceleration of 3.8 meters per second squared. Free body diagram, what is the weight of the object? All right, so we know it has an acceleration of 3.8. We know that combined, we have a net force of FP1 plus FP2. FP1 is 30 plus FP2 is 55. So we have a net force of 85 newtons moving in that direction there. It's important for us to know. Why? Well, because to find, first of all, the mass of an object, the mass of an object is equal to the net force divided by acceleration. I now have a net force of 85, and I have an acceleration of 3.8. Knowing that, now I know that my mass is equal to 22.37 kilograms. Because I have a mass, I can now find my weight, Fg times m times the gravity. So 22.37 times 9.8 gives me 219.2 newtons. If you did the nearest whole number, you would say just 219 newtons. So several steps there to get to the weight. Don't just jump in real quick and just pick a random force. We had to find the net force working in this direction to use to calculate a mass first. And then once we found the mass, we could then use it to find the Fg value. So keep that in mind. There are usually a couple steps here. All right, usually, not always, but usually. Next one. It says the weight of a bucket is 140 newtons. What do you notice about that? Well, one thing I noticed is it didn't say kilograms, did it? It says the weight is in newtons, not kilograms. Ah, okay. The bucket's being raised by two ropes. There's the free body diagram. What is the acceleration? All right, so that means that my bucket has an FG value or a weight of 140. I know this is an FG here, but the bucket itself is 140. So we could say that 140 equals the mass of an object times the gravity, 9.8. So let's divide 140 by 9.8. And when we do that, we find that the mass is equal to 14.28. That is the mass of the bucket. We had to convert the newtons back into a kilogram here. Now that I have it in a kilogram, I can use my acceleration formula and say acceleration equals the net force divided by mass. Well, my mass we said was 14.28, but what about my net force? To find the net force, I need to look at the components going this way and the component going this way. So here I have 95 there, and here I have 10, carry the 1, 120. 120 minus 95 is going to be equal to 25. So my net force is actually 25, and we're going in the positive direction. So we're going to say 25 divided by 14.28. That's my net force divided by the mass, which gives me 1.75, and we're going to say meters per second squared. So a couple steps there to get that one resolved, but you had to kind of work backwards from a Newton, turn it into a mass with kilograms, find a net force, and then once you found the net force, then you could figure out what the acceleration was going to be. Really three different steps to get to that one solution there. Let's try one more problem to wrap up today's review. It says a sled that has a mass of 6 kilograms is being pulled at a 50-degree angle with a force of 32 newtons. So this angle here is 32 newtons this way. All right. The friction force acting on it is 3.8. 3.8 newtons of friction force there. The free body diagram is there. What's the acceleration of the sled? Well, acceleration is always along the horizontal axis. So I know that I have this value as a horizontal one there, but I also have one here when I consider my component parts, right? This is my FPX. I have an FPY and I have an FP right here. So I also need to consider this part here to determine what is my net force, because acceleration is found by the net force divided by the mass. So in order to figure out the net force, I need to figure out what FPX minus FF is to get the net force. So first, let's start with the FPX. The FPX is here. We have a 50-degree angle. We have a 32 value there, and I want this one, which is going to be the adjacent. So the cosine of 50 equals the adjacent, which in our case is FPX, divided by the hypotenuse of 32. Right? That's my 32. Or 32 times cosine of 50 equals FPX. And 32 times cosine of 50 is 20.56. So the value over here is 20.56. So my net force is going to be FPX minus the force of friction. So 22.56 minus 3.8. And 20.56 minus 3.8 is going to be equal to 16.76. Now, if you round at any point here, it's probably going to be okay. I just like to keep the decimals around while I have them because it just helps me keep track of stuff. So now I can use that value to plug it in for the net force, 16.76, and I can divide it by our original mass, which is 6 kilograms there. And 16.76 divided by 6 kilograms is equal to 2.79. And if I round to the nearest tenth, I would say 2.8 meters per second squared. All right, and that's our last one of these for the day. Oh, normal force. Nope, not the last one. We have more to go. Oh my goodness, I thought it was the last one. So let's take a look at now our normal force. Oh goodness. So normal force, we have, do I have more? I do have more. Well, normal force is going to be acting in the upward direction. So my normal force is here going in the vertical direction. And we also have our FG force here going down in this direction. All right, so FG and FN. All right, so to find my force going down, I need to find, first of all, the FG is going to be the weight of that object. So the FG value is going to be the mass of the object times 9.8. Now, the mass of this object is, we said 6 grams, and we're going to multiply 6 times 9.8, and that's going to give us a value of 6 times 9.8, which is 58.8. So that's our FG value, 58.8. To find the Fn, I'm going to need to find the component parts. This is going to be the opposite value because it's across. So Fp, oh goodness, Fpy value, Fpy value. And so because it's opposite, our Fpy is equal to the hypotenuse times the sine of our theta. Our hypotenuse, we said before, was 32. So we're going to do 32 times the sine of 50 for our FP value, FPY. So 32 times sine of 50 equals, in this case here, 24.51. So for what we're doing here, we can say that Fn, which is the positive side, plus Fpy is going to be equal to Fg. Our Fn we don't know. We can go ahead and move the Fpy to the other side by saying Fg minus Fpy. And now let's plug in our values. Fg is 58.8 and Fpy is 24.51. So I do 54.8 and I subtract 24.51. I come up with a normal force of 30.29 newtons, or if you'd had the nearest whole number, you would simply say 30 newtons of force there. So once again, what we're seeing is finite normal force is going to be the combination of this value here and this value here are going to be equal to, when you add them up, to this value here. All right, that's our Fn plus Fpy are equal to the Fg, and that's how we arrive at the normal force. So one final one. So the cart is pulled by a force of 310 newtons at an angle of 35 degrees above the horizontal. So this line here is 310. A cart accelerates at 2.3 meters per second. What is the mass of the cart? All right, so we know we're moving this direction. So we have a horizontal component to this angle right here. And mass acceleration is moving that direction. So the mass of the cart is being found by figuring out how much of the movement is moving in this direction, this FPX once again. So this is going to be our adjacent side. So our FPX is our adjacent side. So we're going to say that the hypotenuse times the cosine of an angle equals our adjacent. Or in our case here, 310 times the cosine of 35 is equal to our FPX value. We're looking for the net force in the horizontal direction, and that's the only force I have to work with. So 310 times the cosine of 35 is equal to 253.93 for our FPX. And if we round to the nearest whole number, we would say 254 for our newtons for our force in the x direction. That's my force there. Now mass is equal to the net force divided by acceleration. So the net force in the horizontal direction is 254, and our acceleration was 2.3. So 254 divided by 2.3 gives me a mass of 110.4, or we could leave it 110 kilograms there. So again, that mass of the cart is found by determining the force, the net force in the horizontal direction, using that net force to calculate mass overall. All right, I think that is actually all for the day. Yes, it actually is. Thought I was done earlier, but there was more. Hope that it helps you study and prepare for your quiz on Friday. Good luck, and we'll see you tomorrow.